So here are some properties, and I'll show you why they work. So the limit of constant is the constant. So if you take a look at this picture, 11 is a constant. Here's what the graph of it looks like. It's a horizontal line. And if I'm approaching any number, right, I'm approaching 5 here. It doesn't matter whether I'm approaching 5 or 8 or 59. This is a constant. There's nothing else that this can possibly equal but 11. All right. And then here's another property. Again, you can take a look at that. If you're taking the limit of x, as x approaches c, it's going to equal c. So let's take a look at what that looks like. This, if you graph it, is this particular line. This is y equals x. And if I'm trying to approach -2, it kind of makes sense. Oh, look at that. The function actually equals -2. There's no holes, there's no jumps, nothing. Okay, so let's take a look at the next one. So if you have x raised to a power, and then x is approaching c, your limit ends up being x raised to c. And here's what this looks like. This is x squared, right? Standard parabola. And if I'm approaching 3, graphically, you know that that equals 9. But that's also the same thing as if you changed, right? If you just plugged that in and got 9. Okay, so what did all these have in common? It's continuity, right? If your graph is continuous at the point you're trying to evaluate the limit, then all you have to do, this will be the easier of the 2 lessons. You just have to do direct substitution. So look at this. I don't have a graph of this, but that's no big deal. I know this is a line. If I did graph it, it would be a line. All I have to do to evaluate this is to plug in 3 in for x. So this limit equals 15. Okay. This. Now, if you think about what the graph of this looks like, yes, it does have an asymptote at -1. Okay. The graph as a whole is not continuous. However, at 2, there's no asymptote. It's continuous at 2. There's no holes, there's no jumps. It works just great. So if you do direct substitution, your calculation is going to look something like that. And the limit is 1. Okay, let's keep going. Okay, so you know what a sine graph looks like, right? A sine graph is just a wave. It is continuous, no holes, no jumps, no nothing, no asymptotes. So I can do this by substitution. All I have to do is plug in pi in for the x value. And so I just give myself a little hint here. Pi ordered pair is at -1, 0, and the sign there is 0. So this limit equals 0. Okay, sort of the same situation here. Maybe you don't know that this is continuous, but you can always check as far as limits first by doing direct substitution. Okay, if you plug the number in and it doesn't give you any issues, right? If there's no zeros in the denominator or negatives under a radical or things like that, right? If it doesn't cause any problems, just plug it in. Direct substitution is always going to be your first line of attack. So if I put 0 in here, the tangent of 0 is 0. 0 over anything equals 0. There's your limit. Okay, and then this one, again, you can pause your screen if you need to take a really close look at this. All it's saying is that if you have a composition of functions, you can either do the limit after the composition, or you can do the limit of just the first function. It doesn't matter. So if you look at these, you could do the composition and then see if 3 works. Or you can just remember that you can do the limit of the inside function first, which I'm going to attempt by direct substitution, which works. If I put 3 into the f function, I get 10. Then I put 10 into the g function, and the answer to this problem is 100. All right. Okay, so then here are some more rules about limits. And they're actually not too difficult if you look at them really close. This one is saying that if you have the limit of the sum of 2 functions, that you could actually take it apart and do the sum of the limits. All right, likewise, if you scoot this up, this is saying that if you have to do the limit of a product, it's the same thing as doing the product of the limits. Okay, scooting it up some more. Here's quotient of limits, right? So if you have the limit of a quotient, feel free to break that apart and do the quotient of the limits, right? One limit versus two. Notice that you can't have that denominator equaling 0, right? That would make something undefined. And then over here, the constant multiple rule. This means that if you have a constant somewhere inside, that you have the capacity to take it out and put it in front. So the limit of a constant times the function is the same thing as the constant times the limit of the function. So that being said, and with all those rules, let's see if we can do these examples. So for the top one, since I have a constant inside, I'm going to pull that out. So this is equivalent to 2 times the limit as x approaches c of just g of x. Now this, I know, right? It's given up here as being 16. So this is 2 times 16 or 32. Okay, so down here, I'm going to do the, instead of the limit of the sum, I'm going to do the sum of the limits, right? The sum of the limits. So I'm going to have 4 plus 16, which is 20. Okay, likewise down here, instead of doing the limit of the product, I'm going to do the product of the limits. So 4 times 16 is 64. And this last one, instead of doing the limit of the quotient, I'm going to do the quotient of the limits, which is 4 over 16, which reduces to be 1/4.